The information contained in these presentations should be considered as general guidance and not engineering advice or services for any particular applications. The opinions expressed are solely those of William G. Beasley and should not be construed to endorse or condone any product, practice, or method. Much of the material was recorded live in a classroom setting and as such may contain unintentional errors and mistakes. In all cases where services to the public are concerned, consult a professional engineer licensed to practice in your particular state or country. Up to the stress. Okay, flange rating. ASME B16.5 has a simple flange rating process. It's a flange rating class. They divide it into 7 classes, 150, 300, 400, 600, 900, and so on. These are pressure and temperature rating combinations for flanges. And since most valves are flanged, then their internal body ratings will follow their flange ratings. Okay, so their internal pressure capability will follow the ratings that you give to their flanges. The flange strength increases obviously with class number, and it's a material and temperature combination without pressure. The material and design temperature combinations without the pressure being shown indicated is not acceptable. How do I find those? That's a table lookup. You find out what material you have, and you see if your pressure and temperature situation is acceptable under the ASME B16.5 system. If it's acceptable, you're done. If not, you have to go to a higher pressure class. That's back here, higher pressure class. Okay. Let's talk about pipe stress. What do you see for pipe stress? Well, occasionally you see the pipe break, but usually what you see is the effect of pipe loads on other things like nozzles, on pumps, pump bearings wear out, pump couplings get misaligned and break. It's a huge maintenance source. If you push the equipment around from pipe expanding, you're going to have trouble. The fix is to put more absorbing leg in. Flanges can leak. You know, you ever see the submarine films where they get depth charges? Boom, the depth charge goes off and all the flanges leak and everybody has to run around tightening them. Well, the reason they leak is because the pipe flexes and it compresses the gasket. And then, you know, now it's leaking seawater and that guy has to go tighten it all up again. Or the pipe permanently deforms. You get creep. There's another condition even more dangerous called ratcheting, where it just keeps yielding and yielding and yielding with every thermal cycle. It never goes back to a stable of deflection. It just keeps yielding and yielding, ratcheting. Okay, the loads on these nozzles, there are standards that tell you what the loads are. You go to those codes, it says you have this kind of standard pump. Here are the loads you get to tolerate. You can't go over these. So every designer that designs a pump says, my pump will take those standard loads. I'll always be able to. I'm not a pipe rack, but I can take at least those loads. How do we decide what pipes to analyze? We get a critical lines list. Distress guy sits down with the client and says, what's the baddest and the worstest? And, you know, okay, I figure out a critical lines list. And those lines are going to have to be checked. Usually he has a criterion. All the rotating equipment, all the lines with nasty stuff in them, hazardous stuff, lines over a certain temperature. He's got a criterion. When you don't have that, you have some tables. Bausbacher and Hunt has some tables that you can look at. Bausbacher and Hunt and other guides usually have 3 standard situations to look at for pipe for which there are closed solutions that give you a way to screen pipe. You don't have to be a stress engineer to find out if you're in trouble with these closed form solutions. And the 3 situations are continuously supported in the rack. It's at least 2 pipe bents away from any exit. So it's continuously supported in the rack. It's bent after bent after bent after bent after bent, and it's just a big droop and droop and droop. So that's the best situation. That is a table, span table. And then they're simply supported. It's getting ready to leave the rack. You're not at least 2 bents away from anything, and now you have to use less span, but there's a table for that. And then finally there's the double overhang. I've got an overhang to go down and an overhang to get to the spandrel. The double overhang is the exit or the entrance. And that they have a graph. but that's also an easy thing to check too. You don't have to be a pipe stress engineer to use those checks. They're right there, set to go. And those are the three common situations you'll see in the rack that we have wonderful solutions for. Now, if you do that check and you don't like the answer, this isn't the right answer, like it doesn't look like it's going to make it, then you go call your friendly pipe stress engineer and say, you know, Houston, we may have a problem, okay? Now, at pumps, remember, pumps are not pipe support, pumps are pumps. A typical situation is to use a kind of a diversion here in the discharge. There's a lot of discharge stuff. There's check valves, block valves, and so on, a lot of pipe. That can weigh 1,000 pounds. So going out the discharge nozzle of a pump, it's not uncommon to have a swing over to one side and have a dummy leg and an adjustable support to hold that pipe up. So now let me just caution you, I've been in this spot where the actual flexion of the pipe actually, instead of being helped by that dummy leg, pivots on that dummy leg and makes it worse on the pump, not better. It actually pivots, it uses it as a pivot. So you actually press harder on the pump than you would have otherwise. So you got to be careful where you put this dummy leg. In most cases, this is a typical configuration you'll see to get out of trouble at the pump. There's another deflection. This deflection is at a control valve station. And it doesn't, this is exaggerated for illustration. Okay, this isn't what you'll actually see. I hope you won't. But just make note that when these valves are twisted too much, they don't work or they'll crack. Okay, or you have leaking flanges. So you don't want a lot of deflection here. You don't want to make it carry a lot of load. And you'll put anchors and guides to make that flex the way you want it. What temperatures to use in pipe stress? Well, first of all, you want to see what the normal operating expand and contract situation is. And then you want to look at the worst case situation, the steam out day. I steam it out today. Okay, that's a higher temperature, or maybe I'm decoking it. Okay, that's high temperature stuff. So am I going to do that a couple times? Maybe that's the temperature I want to look at, not the normal operating temperatures. I've had pipe stress situations where I've had, 10, 20 different operating cases, and I have to check them all. This is on, that's off, they're both on, they're both off. One is turned off suddenly, one is turned on suddenly, that sort of stuff. I mean, you got to look at the worst case. And these loads, here's a API 610. There's API 610 will tell you what the nozzle loads are for their pumps. So if you get an API 610 pump, it's supposed to take these loads. So now you can design to API 610 and you know whatever pump you buy is safe. How do I add flexibility to pipe? I put in a change of direction. The easiest one to put in is a loop, expansion loop. Just change direction in a little off center. That puts in a nice change of direction, and it's nice. You can calculate the size of the expansion loop from a graph. So that's easy to design. But other things I can do is put in more bends, take a more roundabout route. Don't go direct, go in a roundabout way. Put in an expansion joint, which is usually not preferred, but sometimes you just don't have the room. So put in an expansion joint. There's a lot of ways to add changes of direction. And then the other thing is, remember, pipe is a good fishing pole, but it's not a good pogo stick. So I put in guides and anchors to make sure that around the expansion loops, I get the movement direction I want with guides and anchors. Make sure it's a pool shot and not a spaghetti wobble. Okay, it's a pool shot. Okay, make that pipe expand in just the directions you want and control it with guides and anchors. Now, if we get to B31.3, the piping code, it's got some sections. There's a design section, a materials section, a fabrication section, erection, inspection, and testing. All those sections are invoked when they call for B31.3. But most people are interested in the design because at least they want to get the size of the pipe right. Okay. By the way, where's B31.3 called out? It's called out in the material spec. The client says the governing code shall be B31.3. He implies by reference all these issues are satisfied by the designer and by the erector. Okay, now where do we apply it? Well, all the interconnections are B31.3, but inside these particular things, tubes and tube headers and furnaces and fired heaters, no, that's covered by another code. Pressure vessels and heat exchangers and pumps, that's covered by the manufacturer. Packaged equipment, that's covered by the equipment supplier. Boilers and boiler piping, that's covered by another pressure vessel code. So inside the equipment, it's covered by one standard. Outside, it's covered by B31.3. And we look at sustain loads. That's the I'm always going to have it, it's never going away load, like weight of the pipe, weight of the fluid. No matter what happens, you have to remember to hold up the pipe and keep the fluid inside. Okay, if it starts to bubble up or burst out, there's nothing you can do to stop it. It's just going to keep going. If it's too weak to keep that in, or too weak to hold up the pipe, it's just going to keep going and going until it breaks. But the thermal expansion loads, they're different. Those are cyclic loads caused by thermal expansion. If I don't turn the plant on, I don't have those loads. So I can stop that at any time. And that has a tendency, because it's cyclic, the nice thing about steel is it'll yield slightly, and if it yields slightly, it'll relieve local stresses, and then it'll operate, in most cases, unless you get ratcheting, it'll operate in this yielded range of stresses. And those thermal expansion loads are cyclic loads, and that's the one we look at. We base the code on 7,000 cycles. That's turning the plant on and shutting it off once a day, 365 days a year for 20 years. It's about 7,000 cycles. So most of the code fatigue is based on 7,000 cycles. And then we also look at occasional loads. That's the hurricane something or other that blows in, or a cyclone or something like that. Well, earthquakes, those are considered occasional loads. We tolerate a little bit extra stress for that. We just look at yielding failure. And then we always know we do an inspection after that, make sure that nothing got really screwed up. Okay, flexibility and stress intensification factors, different components like elbows, bends, T's, fabricated T's or mitered elbows have different flexibility factors. The way it's referenced, we try to reference it to equivalent straight pipe. So if you have an elbow or a bend, it's more flexible and more highly stressed than straight pipe would be of the same dimension. So we intensify the stress relative to straight pipe. Now the problem with elbows is that they turn into ovals when you bend them. When you have an elbow straight pipe, when it bends, it ovalates like this. It actually, you've seen it in rubber hoses and things like that, where it turns oval and finally it crimps. So it's more flexible but more stressed at the elbow. Same for T's, and you have stress intensification factors.